The first thing we're going to do in order to even start solving these random functions is first narrow down the list of numbers that can qualify as zeros to the function. Okay, so you've seen now that these functions can have any number of zeros, right? And the zeros could either be real numbers or imaginary numbers, like you've seen on the homework several times now, right? So zeros could either be real or imaginary. Now, if a solution or a zero is a real number, again, it can take on two forms, or it could be of two types. It could be a rational zero, a rational number, or an irrational number. So what's an example of an irrational number? What's an example of an irrational zero?
Like negative 5 over 2.
Well, that would be rational.
Like negative 5, square root negative 5 over 2.
Right. So, for example, plus or minus root 5. That's an irrational solution. Okay? Remember, not ones that have negatives inside, because that would be imaginary. So that would be an example of an irrational number. So what about a zero that is a rational number, right? It could be anywhere, anything like x equals negative 1, 5 over 2, negative 3 over 7, and so on. All right. So if we just focus on these rational numbers, how many rational numbers are there in the universe?
Limited.
An infinite amount. Okay, so one way to solve or to find the solutions of a function is to sit there and you just pick random rational numbers, plug them in, and see if they give you 0 when you plug them in, right? So how long would that take? That's really not a very efficient way of solving things. We do, however, have a way to narrow down that list, to get a finite, a smaller list of numbers, rational numbers that could qualify as solutions. Okay, so that's what the rational zero theorem is. The rational zero theorem is going to give us a way to just get a list of numbers that can qualify as zeros to the function. All right, so to do that, we're going to look at two numbers in the function. The first number we're going to look at is the constant, all right? And from that, we're going to extract values that we're going to call p. And another thing we're going to look at is the coefficient of the leading term. And from that, we're going to extract values that we're going to call q. So let's jump in to our first example and see how it's really going to work. All right, so now I have this. All I'm going to do for this function is list all of the possible rational roots. I'm not going to solve just yet, okay? So remember how I said you could either try an infinite number of numbers and see which one works, or you could narrow it down. So let's narrow it down. I'm going to take this number. What's that number? 24, right? But I don't want the 24 itself. I want all the factors of 24, and those are going to be my values of p. So what two numbers can you multiply to get 24? 1 and 24 will work, but how about 6 and 4? Yes, but how about negative 6 and negative 4? Yes? How about negative 1 and negative 24? Yes? So all of those numbers work, including their negative counterparts. So we say, okay, the factors of 24 are plus or minus 1, plus or minus 2, plus or minus 3, 4, 6, 8, 12, 24. We didn't miss any, did we? Now, for Q, I want the coefficient of the leading term. So which one is the leading term?
1.
The x cubed is the leading term, and 1 is its coefficient. So for Q, I want the factors of 1, which would be plus or minus 1. Now, the last step is I want to do P over Q, meaning now I have to combine all the possible pairings for each of the P's with each of the Q's. So I need to get each of the red ones and divide it by each of the blue ones. In this case, I only have one, so it's sort of, yeah, it'll all be the same. So I'm going to do plus or minus 1 over the blue one, plus or minus 2 over the blue, plus or minus 3 over 1, 4 over 1, 6 over 1. So when Q is just 1, you end up with the same numbers as P. Yes.
What is Q with
So how many numbers do I have in that rectangle here? 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16, right? So remember how I said that there were an infinite amount of numbers in the universe that could qualify? Well, I just eliminated a whole bunch and I just narrowed it down to 16. It's still a lot, but it's better than an infinite number to try, okay? So these 16, all of the numbers in the universe got eliminated except for these 16. So the point is, if this function here has rational roots, then they've got to be numbers that are in that list. That's what we just did, okay? All right, so these are all of the possible rational roots. Okay, now, that's all you have to do for that one just yet, okay? Because it said to not solve. So let's do the same thing for this. For P, which number am I going to take? 10. So it's all the factors of 10, which is plus or minus 1, 2, 5, and 10. What number do I pick for Q? 3. And the factors of it are 1 and 3. So for P over Q, now I have a little bit more pairings, right? It's going to be every single one of the red ones divided by every single one of the blue ones. So the way I do it is, I take, Q is the coefficient of the leading term. So what I do it systematically, is I take each of the P's and I first divide it by the ones. So 1 over 1, 2 over 1, 5 over 1, 10 over 1. Then I do the same with the 3, okay?
So there's going to be, all right.
There are going to be, yeah, there are going to be a few more. So plus or minus 1 over 1.
So like all the same one for the first, those are all 1.
Yes.
One, so.
3 over 1. Oh. You always have 1 no matter what the number is, right? Because 1 and itself is always a factor. So 1, 2, 5, 10, that's dividing by the blue 1. And now dividing by the blue 3, it'll be 1 over 3.
Where did you get 1 from?
2 over 3. So I'm dividing each of these, right, by this one. So 1 over 1, 2 over 1, 5 over 1, 10 over 1. Okay? And now I'm going to do each of them over the 3. So plus or minus 1 over 3, 2 over 3. What's next? 5 over 3, and 10 over 3.
It's 16 again.
Right, because 10 had fewer factors than 24. I mean, there is no way to tell. There's no pattern in how many you're going to come up with. Right.
Also 16.
Yes.
I don't quite understand what.
All right. Once you've identified all of the possible ones, the next step then is to take each and every single one of these numbers, test it with a function, and see which one will give you, with the synthetic substitution, a remainder of 0. All right? So you test every single one until you get the first one that gives you a 0, and from there, you stop that process and you'll see that things just sort of unravel on their own. Okay?
So you have to do synthetic division.
You have to do, so you don't have to do it 16 times. You have to start synthetic division, okay? The first one, so chances are, right, 2 or 3 numbers down the line, you're going to find one that gives you 0, okay? It's not going to be the last one on the list.
So 3 of those numbers are going to be 0, right?
Okay, so the process is to test using synthetic division. So remember that if a number is a 0, then the remainder will be 0 when you divide it, okay? Okay, so let's start with this. To guide us, we're gonna do the Descartes rule process. So let's first figure out what the zeros look like using Descartes rule, right? Okay, so the number of positive zeros is how many? Let's see how many sign changes there are here. There is one change there, two there. So it's either 2 or 0. And now let's find f of negative x. So for f of negative x, which one of them are going to flip sign? The x cubed and the 13x, right? So negative x cubed minus 6x squared, positive 13x plus 42. How many times does this change sign? Once? Oh, just once. So the number of negatives are just 1. Okay? So let's see what the chart looks like.
It's not -1 or it's not 1 or 0.
No, because I don't have enough to subtract 2 out of the 1. Okay? So it's either 2 or 1 or 0 and 1. So how many does that leave for imaginary for the first row? 0 and 2. Okay? I have a total of 3. Remember, you can never have an odd number of imaginary numbers. Okay. Now, let's identify the possible rational zeros. So when you hear possible rational zero, just think of P over Q. All right? So let's do the P's. Those are the factors of what? 42. So it's 1, 2, there's a whole bunch.
Just make a plus or minus in the beginning.
Yeah, hang on. 3, 6, right? 7. Those are the numbers that'll change sign when you do f of negative x. So 7, 14, and 21, and 42. So for Q, it's just going to be plus or minus 1, meaning P over Q is all of those red numbers. Now, like I was saying here to Eli, in order to save ink and time and effort, I'll let you put the plus or minus once, and then in parentheses, just list all the numbers.
And that's okay for like when we're listing the factors today.
Yes.
Will that be okay?
It'll be okay everywhere, yes. So those are the possible roots. So now, the process is to take each and every single one of these numbers, do synthetic division, and see which one will give me zeros, right? Now, so what are the numbers I have? I have plus 1 minus 1, plus 2 minus 2, plus 3 minus 3, right? Okay, let's take advantage of Descartes' rule. Sometimes it's helpful, sometimes not so much. Descartes' rule is saying that I have two possibilities for what the solutions are going to look like. I either have 2 positive numbers for the solution and 1 negative, or I have 0 positive and 1 negative. In either case, do you see that you're definitely going to have 1 negative, right? But the positive ones, you're not so sure because you could either have 2 or 0. So since I know I'm definitely going to have 1 negative solution, I say to myself, you know what? Let me just skip over all the positive P's and Q's and just start testing the negative ones. Because I know one of the negative ones is going to work. Okay? Huh? Okay, so we're going to start with -1 and do synthetic division. And I'm going to take the coefficients from here. So the 1, the -6, the -13, and the 42. 1 comes down, right? And I get -1, -7, +7. What do I get here? -6. Does this look like it's going to give me a 0 in the end? No. So I abandon it. And I go to the next one. Right. You can do this part on scratch paper and then copy it over. So here I have -3 now. All right? So before you write it down, let's see if it's going to work. 1 comes down. I have -3.
Why do we skip 2?
-9. Oh, I don't know why I skipped 2.
Okay.
Well, since I started with 3, let me just do it and then I'll go back. What do I get here? 27. What do I get? 14. What does that give me? 0. Hey, that worked. Maybe deep, you know what? It was completely unintentional. It was completely unintentional, but maybe deep down, I just knew. See, the math gods have spoken. Okay? Yes.
Instead of guessing checking, if we already know how to do this part, we just look up.
Okay, so here this is saying use synthetic substitution to find a real root, which we now found. So x equals -3 is a root. Okay? Now it says to examine the depressed polynomial to find the remaining zeros. All right? Okay. From this, the -3, if the -3 is a 0, then what's a factor? X plus 3 is a factor. And this gives me the depressed polynomial. If I started with x cubed, what's the... It's going to be x squared now. X squared minus 9x plus 14. I set that equal to 0. Okay, once I have a quadratic equation, I'm good because I know how to solve quadratic equations. I either factor or I complete the square, which I know you guys love, or we can factor, use the quadratic formula, which I know you guys love a little bit more. So let's do the quadratic formula. X equals +9, because it's -b, plus or minus the square root. Could we have factored this one?
Yeah.
Oh, we can factor this one.
It's x minus 7, x minus 2.
So you can always.
No. You can always factor using P's and Q's. But, okay, so let's factor this one. X minus 7, x minus 2. And I had my x plus 3 from the beginning. You set it all to 0, so x equals -3, +7, +2. And there you have it. Questions. All right, so Descartes' rule. Let's see how many times there is a sign change. For the first case, 0. So there are 0 positive roots. So let's do f of -x. We're going to change the signs of all of the odd exponents. So 2x to the 4 minus 11x cubed plus 26x squared minus 29x plus 12. And how many times does this change sign? Once, twice.
Wait, no, if you turn the negative to the positive.
Yeah.
4 times.
Is this a plus?
Yeah.
Well, it goes negative
4, yeah.
positive 26.
Yeah, it's 4.
It changes every time.
This is 2x to the 4 minus 11x cubed plus 26x squared minus 29x plus 12, right? I thought that was a minus. Okay, so number of negative is 4, 2, or 0.
Why 2?
You take the number and you keep subtracting 2. So -2, -2, -2, -2. When we see Descartes one day, we can ask him, but so far, we're gonna...
I'd like to speak with him.
Okay. So 4 or 0, 2 or 0, 0 or 0, and we get...
No, 0, 0.
So for the p's, it's going to be the factors of 12, so plus or minus 1, 2, 3, 4, 6, and 12. And for q, plus or minus 1 and 2. So now, p over q will be plus or minus 1, 2, 3, 4, 6, and 12. And also, plus or minus 1 over 2. Let me write all this out and then I'll simplify. 2 over 2, 3 over 2, 4 over 2, 6 over 2, 12 over 2. Okay? Now, there are some that you could simplify. 2 over 2 becomes 1. 4 over 2 becomes 2. 6 over 2 becomes 3. That becomes 6. But they're repeating, so you don't have to write them again. So P over Q is plus or minus 1, 2, 3, 4, 6, 12, 1/2, and 3 over 2. Now, it says use synthetic substitution to find a real root, okay? All right. So, let's try one. All right, so it says Descartes' rule says there are not going to be any positive ones, right? So let's go to -1. Let's try -1. I have 2, 11, 26, 29, 12. 2 comes down, -2, 9, -9. What do I get here? 17, -17. What do I get? Or 12. -12, 0. Now, what I have is x plus 1 and 2x to the 3, 9x squared, 17x plus 12. Okay, how do I factor that red one? There is no way to factor. So guess what I have to do? I have to do P over Q for the red one now. Yes, I repeat the whole process. So, when I do P over Q for the 12, okay, I'm going to get the same numbers. Now, we know that there are no positive solutions for this, so I'm going to try the negative solutions, and I'm going to ruin the element of surprise for you. I'm going to tell you the one that works is the very last one, -3 over 2. Okay? It's the math gods. I'll tell you my secret once I do this one. Hang on. Let me finish this, and I will answer all of your questions. Okay, so -3 over 2, okay? You have 2, 9, 17, and 12. 2 comes down. I have -3. 6. What do I get here? -9. What's 17 minus 9 these days? 8. And that gives me -12. Oh my goodness. Okay? No. So now I have x plus 1, x plus 3 over 2, and here I have 2x squared plus 6x plus 8. What type of equation is that blue one? A quadratic. I can totally solve a quadratic equation. I don't need to do anything else. So now, watch. I'm going to write the x plus 1 over. I don't like the way the x plus 3 over 2 looks. We always have to bring the 2 up and make it 2x plus 3. Now, what about that blue equation? Can I factor anything out of it? 2. X squared plus 3x plus what? 4. Okay. Can't factor that one, but what else can I do? Quadratic formula. Okay. -b plus or minus the square root of b squared minus 4 times a times c all over 2. So this is -3 plus or minus the square root of 9 minus 16. Why can't I erase anymore? Yes, all over 2. -3 plus or minus I root 7 over 2. Okay, so finally, what are my solutions? X equals -1, -3 over 2, -3 plus or minus I root 7 over 2. How many total solutions? 4 total solutions. Now, homework is due tomorrow.